All right, so this is a simple chi-square analysis that I'm about to explain here. So this is a chi-square analysis example. Okay, now the reason why you would use chi-square analysis, the chi-square analysis is a good statistical test to check if your observed data, right, your observed data fits your expected data. A lot of times they call it a best fit test. Chi-square analysis test is a best fit test. And with genetic crosses, this is ideal because you really can predict and have expected, very numerical expected results for these fly crosses that you're going to do. Because you can do a Punnett square and you can say, well, if all of Mendel's laws are being followed, I should get this ratio of red-eyed flies to sepia-eye flies, assuming that I'm right about what kind of inheritance they're following and that law of dominance is in play and all of those things are happening, right? So let's take an example. Let's just do the cross. The very first cross that you're going to do is going to be a red-eyed female times a sepia-eyed male. Right? And these are the parents, and the parental cross is always pure, homozygous. So if we have big R for red eyes, then she has 2 big R's. And if we have little r for sepia eyes, then he has 2 little r's, right? And I mean, at this point, you should be able to do this in your sleep. Right? If you do a prediction of this, I'm not even going to go through the Punnett squares because you should be able to do that. Your expected results, right, for the F1s should be 100% big R, little r, right? Red eyes regardless of gender. And then your expected F2, which is what you're going to apply the test to, should be, if you cross 2 of these, right? Meaning if you crossed 2 hybrids, you should get 3-to-1 red to sepia. You should. If everything is just simple dominant recessive, if it's not sex-linked, and if the genes are on an autosome and not on a sex chromosome. That should be your prediction, right? So this would be your expected outcome. Okay. So now how does chi-square work with that? What do we do? Okay, so chi-square has a big, scary-looking equation. And the best way to handle that big, scary-looking equation is to break it down into steps. And the way you do that is you fill in this table step by step. The first thing that you list is the possible phenotypes from this F2 offspring. The first thing that we'll do. Oops, everything good? Okay, yeah. All right, we're going to put observed data in the first column. We're going to put our expected data based on those observed numbers in the second column. We're going to subtract one from the other in this column. We're going to take that number and square it in the next one. We're going to take that number again that has been squared, oops, and divide it by the expected and put it in the last column. Each thing is building on the thing before, okay? All right, So we only have two possible phenotypes. We have red eyes in that F2, in those F2 babies, and we have sepia eyes. And again, in this example, we are not designating male and female as part of the phenotype because we didn't see any evidence that this is sex-linked. So we're looking at this as if it were a simple dominant recessive problem. I'm just going to make up some observed results here, okay? I'm just going to make them up out of my head. Get your calculators out and help me, okay? So let's say that we had 85 red-eyed flies, and let's say we had 20 sepia-eyed, okay? That was what we actually observed. How do we get expected from that? A lot of times this is the challenging thing for students. How do you figure out what your expected would be? Well, you know that you would expect, right, to have it be 3 to 1. Therefore, it's a 4-part Punnett square, right? So we're going to add the red and sepia together to get a total, and we should get 105. I'm terrible at arithmetic, I'm going to tell you that. Graduated from an Ivy League school and I can't do arithmetic. Okay, so 105 total, right? So if that's all 4 parts together, if I divide 105 by 4, that should be my 1, shouldn't it? Which should go here where sepia is. You see how I'm doing this? What's 105 divided by 4? Again, I'm terrible at this. Is it 26? Can we go with 26? You get me that? Okay, thank you, thank you. We're going to go with 26 and round it a little bit. All right, so if this is 26 and that's my 1, right? How do I get my 3 up here? I multiply 26 by 3. What's 26 times 3? Thank you. So we're going to go with 79. Okay, excellent. You don't need those. I was just putting those there for reference points. Okay, so if you had perfect 3 to 1 ratio with this many total flies, you should have gotten 79 red and 26 sepia-eyed. So you see there's a bit of a difference between your observed and expected. The question is the difference great enough to say, no, this isn't following Mendel law? Or is the difference slight and small enough to say, oh no, it's okay, we can accept that Mendel law was followed here? That's the question. All right, so observed minus expected, we'll go with that. 79 minus 85, that's 6, right? Actually, it's negative 6, and then here it's positive 6, right? Okay, so there's how you get the next column. I take that and I square it, and I should get 36. Please tell me if I make a mistake. Okay, 36 there, right? Because I squared that. Now I'm going to take 36 and divide it by the expected for red eyes, which is 79. And I'm going to take 36 here also, but I'm going to divide it by expected for sepia eyes, which is 26. Okay, can you guys tell me what I get for each of those? You know, I can do it. I probably guys are quicker. Okay, yeah, I'm getting 0.45, yeah, good. So let's go with 0.46 here. And what about this one? 36, oh, 36 divided by 26 is going to be greater than 1, right? 36 divided by 26. 1.38, right? 1.38. Is that right? I think so. Those both look about right if I'm looking at it. So, all right. Okay, now the final calculation to get a chi-square value, final calculation, is that you take these two numbers and you add them together to get your calculated chi-square, which is going to be, it should be 1.84. 5. Are you guys getting the same number I am? Hope so. Okay. Hope so. All right. All right, so my chi-square value from my data is 1.85. You don't have to go any further. Chi-square does not mean you have to take the square root to solve for x. You don't have to do that. X squared is the symbol for chi-square. That's the actual variable. You don't have to do anything more to it. You're finished calculating. Okay, it's actually just, that's what it's called, all right? So that's your calculated chi-square that's from your data. Now, that doesn't mean anything unless you compare it to a table. All right, so now, if you'll excuse me, I think I can do it right here. Sorry, I should have done this before. Let me insert. I can find it here. Yes. I'm actually organized. Yes, yes, chi-square table. There we go. Ha! Here's the chi-square table. Okay, look at that. So now I have something that I can look at, and there's a couple of things I need to do. So I want to compare my number, 1.85, to a number from this table that fits the same parameters as my study, as my experiment. So there's two things you need. You need something called, let me just make this small. You need DF, which is, oh, what is going on with this? This is not working at all. Okay, never mind. Cut that. Thank you. It doesn't like that. It didn't like that. Just wrap this there. There we go. That's better. All right, I think that'll work now. All right, you need something called DF. It's doing it again. This thing right there, DF. That's called degrees of freedom. And the degrees of freedom is the number of phenotypes, the number of different phenotypes in your table up there. In our case, we had 2, right? Either red eyes or sepia eyes, minus 1. So 2 minus 1, degrees of freedom is 1. There's 1. So look along the number 1. This is the column. This is the part we want right here. Okay. We'll look at one of those numbers. The next thing we need is a p-value. And I'm going to try to explain this well to you. I'm not a statistics teacher. I'll do the best I can. The p-value is answering the question, at what level, how much confidence do we want to have in our comparison? So how certain do we want to be that either Mendel law was followed or not followed? And you're always going to use, unless they tell you otherwise, you're always going to use 0.05, which means that you can be 95% confident that your data fits, right? That your data fit the expected. That's all that means. So if we're in that region, then here's where we are, and that's the number we're looking at right there. 3.841, and that is our critical value. That's what that's called. So if we compare these two numbers, the number you calculated with all that malarkey in the table, right? And the critical value that we got from a probability alpha table. What we say is, if your number that you calculate, if this number is smaller than the critical value, you can accept your null hypothesis. In other words, happy day, your data is a good fit. That's what that means. That means that the difference between your observed and expected was small enough that it didn't overflow the critical value. You can kind of think of it that way. That there's only about a 3.841 value of wiggle room that you're allowed. And if you get more than that, if you calculated like 4.2 instead of 1.85, then you would have had to say, no, the difference between observed and expected was too large, and we have to reject null hypothesis. Okay, and that's just one simple example, and I'm sure you're going to have questions, and I think Mr. Anderson will help with his video as well in understanding.